Hello! In the last episode, we set up an SDL2 window for OpenGL in Rust, so now we can dive in the core of OpenGL, the graphics pipeline or rendering pipeline. The goal of OpenGL and other graphics APIs is to make use of GPUs, graphics processing units, if available, for high-performance rendering. This is what makes your games, applications, videos, and screens refresh at a high rate, making those smooth to the eye. The power of GPUs lies in their capability to execute a huge amount of simple operations simultaneously. In OpenGL, a program that runs instructions in parallel on the GPU is called a shader, and this particular sequence of shaders is the graphics pipeline. Its goal is to render pixels to a frame buffer which stores pixel color data that will be displayed on the screen. A few shader stages are optional, like tessellation and geometry shaders, which will be the subject of future videos. And some other shader stages are non-programmable, which means OpenGL doesn't enable us to write these shaders. Only the vertex shader is required to be written in the graphics pipeline. For now, we'll focus on the vertex and fragment shaders. In OpenGL, things that contain state or data transmitted to or from the GPU are called objects. This includes shaders. Let's create a new file, objects.rs, that will centralize the code for OpenGL objects and simplify the code written in main.rs. Import a few structs and functions that will be used a lot. Create a struct, shader, that will have a field ID of type GLUint for GL unsigned integer, which is the expected type of OpenGL shaders. Along with shaders, create a struct, program. An OpenGL program is a group of compiled OpenGL shaders, and it is what we bind in order for our shaders to be used. Add a method from source to the shader struct. It will take in the source code for the shader as a C string and the corresponding shader stage, a GL enum. It will create, source, and compile the shader before checking whether an error occurred while compiling. If it did, get the size of the error message, create a C string of that size, fill it with the error message, and return it as an error to make Rust panic. If it didn't, return OK with an instance of the shader struct. Note that we use C-string as it is the format in which OpenGL returns strings. It is null terminated, meaning it ends with a null character, a 0 in the ASCII table. Add another method to shader simply to retrieve its ID. Implement the drop trait for shader, which will tell Rust what to do once a shader instance goes out of scope. We will use it for most OpenGL objects, those which require to be deleted to free the memory they used. Now on to the program struct. Use the drop trait to, this time to call GL delete program. The program struct will have a method from shaders that will take in a slice of shader instances and will attach each of them to a newly created program. Try linking the program and perform similar error handling as in shader. Create a public function, createProgram, that will use the code above to create a program out of shaders from the main thread in one function call. Inside, instantiate vertex and fragment shaders from source. The source code of shaders is written in GLSL for OpenGL Shading Language. It is a C-like language, and it doesn't have standard file extensions. I will call the files .vert and .frag. The first thing to write in a shader is the GLSL version and profile we want to use. make them correspond to the OpenGL version and profile you are using. I have set up OpenGL 3.3 core in the setup video, so in the shader I can write #version 330 core. The vertex shader takes in a number of vertices with some arbitrary data we will later set to be a vec2, vector of two floats, containing the x and y position of points. This position is specified in normalized coordinates, which represent any point within the viewport with an x and a y value both between -1 and 1, from left to right and from bottom to top. The position data we'll give to vertices will be the first and only location of the vertex data layout. Then write a main function. This is what will be executed in parallel for each vertex given. Return a vec4 with the x, y, z normalized coordinates and a w value or fourth value of 1. With the same first line from the vertex shader, write the fragment shader. It will run on each fragment within a primitive. A fragment is a point in the viewport to which a color will be given in the fragment shader. There is typically one fragment at the center of each pixel. A primitive is either a point, a line, or a triangle, and was assembled after the vertex shader. We will stick to triangles for now, they are the most useful to draw surfaces and models. Name the output of the fragment shader, like color, and set it to a yellow value like the sun. Back to main.rs, call createProgram from here. Add another method to program, set, that will call GLUseProgram to set this program as the current one. It can be good to separate it from the creation of the program, as in a bigger project you may have several programs to bind one at a time. Finish writing createProgram and use this program in main.rs with program.set. Now we need to specify the input data of the program. To do that, we'll create another struct for vertex buffer objects, or VBOs, which will also contain an ID of type GLUint. A buffer is a memory storage accessible from the GPU. The VBO is the buffer that contains vertex data given as input to the vertex shader. VBOs follow the standard object model, which means they must be generated once before use and deleted once after use, and can be bound and unbound to their specific target, which in the case of VBOs is GLArrayBuffer. Implement the drop trait for VBOs too, to unbind and delete them when they get out of scope. Then, in order to write data to this buffer, bind it and call GLBufferData with the GLArrayBuffer target, the size of the buffer data, which are vertices in memory, a pointer to the vertex data we passed in the method, and a usage hint. You have 9 possibilities for the hint: stream or static or dynamic, and draw or read or copy. In our case, we will set the VBO data once and use it to draw every frame, so the token we will use is GLStaticDraw. Make sure the data you provide matches the types in the GLSL code. Rust F32 is the same as GLSL float with the default precision, which we didn't change. And a vec2 is just 2 floats in memory, so everything should be right. Inside VBOs, we will tend to find many times the same vertices, most likely when triangles are conjoined. So instead of repeating them, we can have an index buffer object, or IBO, that will index the VBO. Using IBOs is known to be generally faster. IBOs also follow the OpenGL object model. Copy the code from VBO, as it is very similar, and change the target to GL element array buffer, and the input data to indices of type U32, unsigned integers. The last thing we need to do is to describe how the input data is laid out. This is the purpose of vertex array objects, or VAOs, which once again follow the OpenGL object model, this time with vertex array instead of buffer as function suffixes. Replace the data function with a setup function that will call GL enable vertex attrib array 0 to enable looking for location 0 in GLSL, and GL vertex attrib pointer with that enabled index 0, the number of values at this location 2, one for x and one for y, the data type floats, whether to normalize them false, as we'll already provide normalized floats, the stride or offset between location 0 of the first vertex and location 0 of the second vertex, which is twice the memory size of a float, as we have 2 floats per vertex, and the offset of the buffer from where this layout applies, 0 or null, as we start from the beginning. Summarizing what we can do now. We can call GL draw elements, which will launch the program with the input data being the bound VBO and IBO laid out as specified by the bound VAO. This input is sent to the vertex shader that will use the 2 floats of the vertex they run for as positions for the vertex to be placed on the screen in normalized coordinates. The fragment shader will then set every fragment inside the triangles formed when assembling primitives to a yellow color. Every frame, the frame buffer that is finally written to, will be swapped with the currently displayed one so we can see it. Okay, so let's first see a basic triangle. Set vertices to 6 floats, or the xy coordinates of 3 vertices. Set indices to 0, 1, 2, as we want our triangle to have its points defined by those 3 vertices. Generate a VBO and set its data to these vertices. Generate and set a VAO. Generate an IBO and set its data to these indices. And in the main loop, call GL draw elements in the mode GL triangles for a number of indices equal to the length of the indices vector with the index type unsigned int, which is the same as Rust U32, and an indices pointer set to null to use the bound IBO. Try running, and unsurprisingly I missed it. Okay, that was just the W value of the vertex that was set to 0 instead of 1, which moved every vertex to the middle. And voila! The sun is a triangle. Now that it is working, let's go a bit further by creating other regular polygons. First, replace the vertices and indices vectors to be the output of a function, triangle fan. A triangle fan is a group of adjacent triangles sharing a common vertex called hub. To draw a regular polygon of n sides, we will create a triangle fan with its hub at 0, 0 and n other vertices placed regularly on the unit circle, downscaled by half. Try for 3, 4 vertices. We can automate that. Every second that passes, add one more side to the polygon by resetting the data of VBO and IBO. This seems to be eating the sun more than rounding its edges. First, I forgot to change the usage of buffers to dynamic draw, as we set the data more than once. And I used the indices variables defined at the beginning instead of the new one, which is now out of scope. This only draws the maximum of 12 initial vertices. And that's it for the basic graphics pipeline. I hope you enjoyed this and learned something. See ya!